So good morning, good afternoon, good evening, everyone. Thanks, Lino, for the nice introduction. As Lino said, we use the BayesiaLab software to conduct the BBN model, Bayesian Belief Network model at P&G for all kinds of reasons across R&D, commercial, and even process in different business units, different organizations at P&G. So today, basically, we wanted to share our learnings on driver analysis using topics derived from unstructured textual data. So we know traditionally in the BayesiaLab or building a BBN model, we can build a BBN model really easily using BayesiaLab. If you have a spreadsheet, if you have your data represented, numerical data, discrete data represented in a spreadsheet. But in this context, this is the data from, let's say, consumer survey, from blind test survey, from identified product test survey, etc. But these days, we have so many unstructured texture data. They're essentially ubiquitous and represent voice of consumer. Such texture data could include, let's say, consumer reviews on Amazon, or even consumer comments in our own website, or consumer comments in your survey. You ask some open-ended questions, usually in the survey, consumer give you some verbatims. So these are all the examples of raw texture data. And we believe this kind of data represent a voice of consumer, a lot of consumer insights, or even product innovation ideas can be identified and should be identified from this kind of data. So the general procedure to model this kind of data, to build a driver's model using this data, is you first need to convert this unstructured texture data into some structured data. So the typical way you can do that is you can use a topic model relating to directly allocation if you are using in Bayesian framework, or some popular deep learning model like BERT topic can also help you to convert, let's say, consumer review, each of the consumer review into a structured topics or sentiment. Essentially can convert that, whether you have topic A to topics, all other topics, etc. And also give you the sentiments, right? So traditionally, that's what people do text analytics. So the question is, you have the topics, you have the sentiments, so what, right? This topic themselves and sentiments themselves will not help you that much to unlock the product innovation. So here, topic sentiments is like we try to, rather than just have topic and sentiments, we wanted to have a way to understand the drivers, the relationships among the topic. That's the thing really matters. Otherwise, topics themselves, sentiments themselves will not help that much. So that's why we try to build a Bayesian belief network model on top of these topics and sentiments, so that number one, we know the relationship among these topics. And we also wanted to know what are the drivers, what are the topics drive, let's say, star rating or purchase propensity. So that's the a general idea. Of course, the main challenge is a higher missing rate is the main challenge to build a Bayesian belief network model on topic data. Imagine, you can think of this on Amazon review, each of the review probably just talk about one topic, or at most maybe 3 topics. Most of the review may don't even have a topic. They just say, love this product so much, and then, give a rating. So in this sense, there are huge missing data in your table. Each of the row, you essentially only have few topics, few sentiments. So this presentation going to be specifically focused on how do we handle this higher missing rate, what kind of method we should use if we wanted to build a driver model to analyze the unstructured data. The different missing mechanism, like in the context, the unstructured data, let's say the consumer review data, right? On Amazon, if the data is missing, there could be all kind of reasons why these topics are missing. It could be a consumer doesn't like something, they don't bother to comment. It could be also the opposite, right? They think this product benefit, let's say cleaning power, is good enough. They don't want to comment on the thing they already get the job done. They want to comment on something that cannot satisfy something. It could be also neutral, right? Doesn't matter. So there could be really different missing mechanism. We don't know. Without knowing missing mechanism, it's really hard to do any imputation. So these are from the BayesiaLab, the white book, the pretty much. If you attended a BayesiaLab conference in the past, you probably have this book, or this is the online version. So the missing mechanism could be totally missing at random. It could be missing not at random, meaning the missing depends on the observation. But the example in the white book is really nice. So essentially, the key idea is if you don't know the missing mechanism, what are you going to do with this higher missing rate? What BayesiaLab recommended, you can use approximate dynamic imputation. Of course, if you have the computational power, you can also use dynamic imputation. At high level, you can think of this as something like a YAM algorithm, the expectation maximization algorithm. You first learn a structure. You just, let's say, randomly give a value to the data and then learn the structure. And then from the structure that you impute the missing value. And then based on the new imputed missing value, you learn the structure again. You keep doing that. Called the dynamic imputation. It will really like a kind of computationally expensive. So if you do approximate dynamic imputation, it will imitate the process, if I understand it correctly, right? So essentially, this is the way if you don't know missing mechanism, you can do this. So the third way is you can simply say, I don't know the missing mechanism. Let's just treat that as a filtered state. Filtered state is something like not applicable. The example could be, say, you ask a survey, right? You do a survey on a different hotel, the example used in BayesiaLab, the white book. If you try to ask what consumers' perception on the swimming pool, and the hotel doesn't have a swimming pool at all, the question is not really applicable to this hotel, right? So there's going to be a filtered state. If you think of the consumer review data, the thing we try to build a BBN model on either topic, let's say sentiments, right? You want to try to say which topic sentiments will drive star rating. The thing is, if the consumer never mentioned the topic, and then you have no way to know the sentiment of a topic, right? So it's a kind of something not applicable. Of course, these are one of our assumptions. So another way we call it method 4, right? Another way you can think of, we treat this as a special category. Let's say you simply think if consumer never mention something is neutral, they're neutral about this topic. We also do this kind of thing, do the comparison. You essentially replace all the missing value, let's say with something neutral, with a neutral value. If you use -1 as negative, 1 as positive, the neutral could be 0, right? So these are the different methods we use. And then before we go to the simulation, all the data we will see will be purely based on simulation. Apparently, I cannot use the real data. So this is the way how you do driver analysis and the impact analysis, right? You first learn the model from the data, and then you calculate the mean value curves. Mean value curves meaning how many changes each of the change in other nodes will cause in a target node. In this case, this one, the player, right? The drivers, the total effect is essentially you can think of the partial derivative, or literally the delta y divided by delta x. The standardized total effect is drivers. The total effect is normalized by the standard deviation. Essentially, you normalize the total effect by using the uncertainty, using the spread in the observation itself, right? And another concept, this is for the overall model. You build a model on all the data. Another concept is called impact. Impact is after the drivers in the whole category, let's say shampoo, right? The drivers in the whole shampoo category, you wanted to know for a specific brand, what are you going to do? What for this specific, let's say, Head and Shoulders, which product benefits is winning, which is losing. So we do this by essentially total effect. Let's say it's this one. You calculate it from the overall category model, right? We presented this a long time ago, maybe 2018, 2019. I couldn't remember. So this is from the overall model. And this one, A and B is the benchmark base, right? Let's say you, by default, you can use the average, marketing average, meaning the average value of the some sentiments from the whole category. And the A could be the product you try to understand, let's say Head and Shoulders. And then mathematically, this roughly equal to target. So we're going to calculate, we mainly concern two things, the drivers and the impact on the specific product. Also, you can go to the white book for details. So these are the simulation, really a simple simulation we did, right? So you can manually construct a network like this. You can link some, give a structure like this. And also you can manually input the underlying probability table, the conditional probability table here. In this case, we intentionally try to say F1 and F3, since we can manually input the probability value there, right? We say these two are the positive drivers, and F2 and F4 are negative drivers. And also F5 is not connected at all with the other part, right? So it's not relevant. And the sample size is, once you specify the conditional probability table, you can generate the sample data, which will like consistent with this, with the model, the ground truth model you specified, right? So you can use this model to generate a hypothetical data, the simulation data, 10,000 data points, let's say. We also have a branch variable. It's a breakout to try to understand the impact on each of the branch later. They have different sizes. Two brands have really relatively larger size. Two brands have a smaller size. And then the missing data generation, once you generate this hypothetical simulated data from the ground truth network, right? We will ask 1 to F5 missing completely at random. And let's say in the context of consumer review, the brand you will know as long as the consumer give you a rating, right? So no missing in brand. And the missingness in target is decided this way. If F1 and F5 are all missing, and then target is missing. Because this is, let's say, if they never mention any topic, right? There's no overall sentiment at all, or no star rating at all. That's the assumption. We have some high level metrics, depends on the topics. You at least need one topic to have the overall metrics. Let's say, for the sake of this presentation, let's say this is star rating, right? So these are the setup of the simulation. So what we try to do next few slides, we try to say, using different missing data handling methods, which one can recover the ground truth, which one can recover the drivers, recover the impact setup. So here is a higher missing rate, right? This is, let's say, 80% of the data missing. Again, at the top row, these are the network structure learned from different methods. And this is the ground truth. So you see method 4 is the filtered state. You can see from this sample. So this one is the ADI, the Approximate Dynamic Imputation. So this one is you simply, let's say, replace the value with a special category. That's a neutral value, right? So apparently the first observation is if you simply make a strong assumption that if consumer don't mention something, meaning they are neutral about something, you tend to learn a lot of curious structures like this too. It's not appropriate to conduct a driver analysis. Apparently, you see the drivers, they're totally different from this three. So the method 4, these are the, simply use this as a filtered state. And the ADI, if you wanted to impute the missing value, right? Their drivers and impacts are consistent with each other and in line with the ground truth. If you compare here, I've got one link was missing because remember, F4 you see here is the weakest link. If you read the earlier part, F4, they have impact through F3 and the F2, right? They're really weak links. So this F4 was not picked up by at higher missing rate by these two measures. That makes sense because you have so many missing data here. And when we do impact analysis, apparently this one, the drivers is not reliable right here. And the impact analysis relied on the total effect here from the drivers. So we didn't even bother to calculate it. You simply cannot calculate impact using this way. We do have internal methods also try to mitigate this. We will not be able to disclose that. But if you purely rely on BayesiaLab, it seems measured for and the ADI, the filtered states and the approximate dynamic imputation, the impact, if you benchmark your brand A versus overall, meaning the category average, the market average, right? See brand A, which attributes you're winning, which attributes you're losing. These are the ground truths. These are the recovered from the measured for and the ADI. They're quite consistent, essentially, other than one weak driver was not picked by the data, by the model. So and then if we wanted to, the same thing, higher missing rate, right? 80% missing. If we wanted to benchmark brand A versus brand D, remember, brand A is a smaller brand. Brand D is a larger brand, right? So if you larger base size, so when you try to compare a product with a benchmark of large base size, there's a product D. The impact of measured for and measured ADR, they are quite consistent. They're consistent with each other and also in line with Ground Truth BBN network. So the issue is if you wanted to compare benchmark brand A versus brand B, both brand A and brand B, they are smaller base size, remember, in the earlier simulation. So this will cause the issue because let's say this is the ground truth, right? So this is the result from filtered states, result from ADI. You see, again, the ADI and the measured for they are essentially the same, consistent with each other. They're different from the ground truth. One thing is you miss one thing, and also, the F3 is just directionally wrong. And this is the biggest impact. This is not the thing you wanted to see. So the takeaway here is that if you wanted to calculate the impact of a brand, benchmark your brand, right? You better have a benchmark base, have a larger base size, either a larger brand or the market average. So if not, either ADI or the measured for will not be able to recover the true impact. Assume these are the missing, you don't know the missing mechanism, right? Either you do imputation or do filter states, you will have trouble to do that. And then we also investigate, I don't know, how do I make this go away? At medium missing rate, meaning if the missing rate is 40% to 60%, right? Again, you see, because you have less data missing, the method 4 and the method 3, they can recover. Essentially, the structure here is, you can think of equivalent, right, to this one. And then you calculate the drivers in the middle row. They are like method 4, filtered state, and ADI. They're consistent with each other and also consistent with the ground truth. You can recover the drivers and the equivalent structures. Again, so method 3, you got this spurious link like here or even here. And the drivers you calculated, again, they're misleading if you simply replace the missing data with some strong assumptions. Again, we didn't calculate the impact in this way. So this, again, is you benchmark brand A versus the overall, the market average, right? The market average, you have a lot of data. You can recover the impact. And then at medium missing rate, if you wanted to benchmark this again, calculate the impact of brand A versus brand D. Brand D is a larger brand, right? Again, you can recover the impact versus the ground truth. They're quite nicely. I didn't show brand A versus brand B. If you do versus brand B, you're gonna have the issue. Some of the impact will flip sign essentially. So then, at the lower missing rate, we also try, let's say if you only had 10% missing in your data. So this, the top row against the structure, you see all the methods at the lower missing rate. Either you do imputation, filter state, or you simply replace the missing value with the data. It will be, they're all recover the true right structure of the ground truth. The drivers measured for the filtered state and the ADI, they're consistent with the ground truth. And the method 3, interestingly, even you can recover the structure, you will not have the right set of drivers. Totally makes sense because the drivers, the standardized total effect rely on the value, the delta X, right? If you just have 10% of missing, you replace all this 10% missing with a given value, with a, let's say, neutral value, right? It will affect the calculation. Essentially, the drivers are not correct, not in the right order. So again, we didn't calculate the impact in this method. So at the lower missing rate, if we compare the brand A versus brand B, the smaller brand, again, you see the flip sign of the impact F2, right? It's just because you can't use even at a smaller missing rate, you better use a benchmark which has larger base size. That's essentially the takeaway message. So here are the major takeaways. Without knowing explicit missing mechanism, BayesiaLab recommend you use ADI. So with complete and missing simulated data, in our case, filtered states and ADI tend to learn same or very similar model structures, drivers, and impacts. At a lower missing rate, structures, drivers, and impacts are same as those from simulated ground truth. At medium missing rate, they also tend to be same or very similar as the ground truth model through equivalent model structures. At higher missing rate, they tend to recover most of the correct structure, drivers, and impacts. So that means the implication is that if you really wanted to deal with this higher missing rate, probably either use ADI or filtered states. They're good. You don't replace the missing rate with a single value. So method 3 tend to learn more spurious structures, as we saw. If you replace that, that's going to be the same. These spurious links also cause these drivers quite different across missing rates. We saw in different missing rates. And also when conducting impact analysis, overall category average seems a better basis to compare with. This is because, overall category average are less sensitive to missing caused by random sampling or other mechanism than that of an individual product leg. So yeah, that's the takeaway.